Hi, everyone, and welcome to this episode. In our last episode, we learned about heat of fusion and heat of vaporization. And we learned that heat of fusion is the extra energy required to melt a gram of a substance at its melting point. And that energy is extra because it goes into breaking the attractions between the molecules. And heat of vaporization is the extra energy required to vaporize a gram of a substance. And that also goes into breaking chemical attractions between the molecules so that they can fly around individually of each other. And today we're going to do a couple of quick calculations based using heat of fusion and heat of vaporization. And my inspiration is a bottle of water, a standard 500 milliliter bottle of water. It's wintertime, and imagine if I take this bottle of water outside. Inside here it's 21 degrees. Outside, maybe it's minus 12 overnight. And I let it sit there and it freezes overnight. How much energy will this bottle of water lose on its way down to minus 12? We can calculate that. And it actually is going to take us 3 steps. And when you encounter problems like these, uh, I want you to be thinking about the questions we've been practicing and asking ourselves. First, when you read a question like this, is there a temperature change? And yes, there is definitely temperature changing going on. Is there a phase change? And yes, because we see this word froze. When you see those words like freeze or melt or boil or condense, those are phase changes, and you want to actually use the heat of fusion and heat of vaporization for those. And in fact, I want you to imagine a heating and cooling graph for whatever substance your problem has in it. In this case, it's water. And that heating and cooling graph has typically 5 line segments in it for a substance. You'll have one for the heating of the solid. At some temperature, you're going to have the melting, and for water, it's at 0. Then you're going to be heating the liquid. Then you're going to be boiling at some temperature, whatever unique temperature that substance has. And then here you have the vapor. And it's helpful to sort of travel along the graph here to see how many line segments you're going to have to go through. Now, if I'm starting at 21, which is somewhere around there, and I'm getting down to minus 10, which is somewhere around there, I actually have 3 segments. First, I have to cool it to its freezing point. Then I have to freeze it. And then I have to cool it down a little bit further. So that's 3 separate steps in this problem that I have to do. So let's get into it. A lot of people recommend, and so do I, sort of mapping it out. So using Q as our letter for heat, Q total is going to be equal to Q1, which is for cooling to 0. All right, that's my first Q. That's what I have to calculate first. Then I'm going to add to it the heat I would get from freezing it. And then I'm going to add to it the Q that I get from cooling down to minus 12 degrees Celsius. That's 3 different things I have to do on this problem. So once we have our Q's sort of set up, I got 3 things. I'm going to actually start substituting in the Cm delta T or the other one. Now this cooling is a temperature change, so I'm going to put in a Cm delta T plus the Q of the freezing. And we learned that for freezing, we want to use the heat of fusion times mass term. And then we have another cooling to minus 12, so Cm delta T again. Okay, now it's time to plug in a bunch of numbers and start calculating. So Q for the first one. The heat capacity of water is 4.184 joules per gram degree. The mass, okay. The mass here, I have a 500 milliliter bottle. And this can be tricky for some people, but it's actually, once you know it, it's not that tricky at all. Water has a density very close to 1 gram per milliliter at normal temperatures. Okay. And so a good assumption is if you have milliliters of water, just change it into grams of water. It might not be completely exact, but it's really, really close. So let's put in 500 grams of water. And we're going to do final minus initial. So for the first segment, the final is 0. All right. And that'll give us a negative value, which is okay because we're losing heat. That's a directional negative. And then for the next part, heat of fusion of water, we learned is 334 joules per gram. again, times 500 grams. And the last part we have the, actually I'm going to do this down here so I can keep it in the field of view. 4.184, oh, actually, sorry, apologies for that. It turns out, I don't know if you know this, but ice has a different heat capacity than liquid water does. That's just because of the structure of it. It actually has a heat capacity of 2.06 joules per gram degree. You could look that up on the internet. You don't have to memorize that. And the mass is 500 grams. And we're going down to minus 12 from 0. Okay. And that'll give me another negative. Now, this product here is going to give me a positive answer, but I'm actually going to make it negative because of the fact that I know that when it's freezing, it's going to be losing its heat. So it's a directional negative again. And so my 3 Qs, I got a Q total of, for the first part, 43,932 joules. For the second part, the freezing part, 167,000 joules. And for the third part, 12,360 joules. And I'm going to round my final answer. So I'm going to add those together. And that gives me 223,000 joules. So I'm going to round that to 223. There's other numbers there, but I'm just going to keep 3, or 223 kilojoules. And which is kind of cool to be able to think about. So if I actually take this bottle of water outside and leave it there overnight in the winter, it will lose just over 200 kilojoules of heat on the way down. And you can't see that heat, but you can see the effects of that heat leaving. And it's pretty cool, I think, to be able to calculate that. Okay? Now, it's your turn. I have one prepared for you to try. If you feel so led. It's a related example, except we're going the other way. What if I take 200 grams of ice at minus 40 degrees and I brought it inside and I allow it to melt and warm to 25 degrees Celsius? How much energy in joules would it absorb? Take a moment, if you feel so led, to calculate this, and pause the video and come back and see the solution. All right, if you did this calculation, congratulations. That's extra nerdy of you. And I'll show you the solution that I got. I got a little over 100 kilojoules, which is about half of what my first one was, but I'm using only 200 grams of ice and a similar temperature change. So Cm delta T to heat it to 0, heat of fusion times mass, Cm delta T to heat it to 25. And these all end up positives because we're gaining heat in the positive direction, and it comes out as 104 kilojoules. So there you have it. Working with heat of fusion and heat of vaporization, you just have to treat them in sections and get a total at the end. You'll probably see some of these in your chemistry travels. Okay, that's it for this time. And if you have any questions or comments, you can put them